So today we will continue in the concept of center of mass. This is a point where the mass of that body, it is assumed to be centered, it is assumed to be concentrated, and we have different formula for derived for two body system and three body system. So for two body system we have this RCM, it is equivalent to M1x1 plus M2x2 by M1 plus M2, and for three body system this RCM, this is for two body system, and for three body system this is equal to M1x1 plus M2x2 plus M3x3. I should take this is R, so this is R1, this is R2, and this is R1, R2, R3 by M1 plus M2 plus M3. So x1, x2, x3, these are the coordinates along x-axis of this mass M1, M2 and M3. And here I have taken this in terms of R. R is that the vector in vector form. So this is the vector, and if this M1 it is equal to taken as equivalent to M, then this RCM it is the just average of R1 by R2 by this, and this if this is M1 it is equivalent to M2, it is equivalent to M3 is equivalent to M. Means that all particles are identical in case of mass. So this RCM this is equal to R1 plus R2 plus R3 by 3, and for n particle system, this RCM it is equal to M1 R1 plus M2 R2 plus M3 R3 and so on Mn Rn by M1 plus M2 plus M3 and so on. This is Mn, and one can write this is in terms of summation, this is M1 R1 in terms of I by summation Ni, where this I is taken from I is equal to 1 to n, and one can also write this is equal to summation of Mi R by capital M, where capital M is the combined mass of all, the combined mass of that system of n particles. So this is simple cases where we have taken this mass as a discrete. Discrete means it has individuality. We can take individual particles as M1, M2, M3 and so on. If we have a compact system that is known as a rigid body, so now we will extend this case in case of a rigid body, where that have a rigid body having n numbers of particles, and that rigid body and the density is identical. Conditions are if density is identical. Also, let's say mass of particles, mass of constituent particles are identical. Density is uniform. I should write not identical. So if density is uniform, everywhere it is same, and the mass of particles these are identical. Means if we have n particles and each particles is of mass m, and body is rigid means the position is unchanged, it's fixed. So position is unchanged. Then we use some other method of formulation. What we will do, we can use that conventional method of summing as a summation, or conventional method, phenomenological, if one term is used, method of calculation. What we do, we just take the small part, or we subdivide the small part of this rigid body in small segments having the mass delta m. Why so? because in the concept of that center of mass, what we have taken so far, this is that mass m1, this is another mass m2, and we need its coordinates. So in case of rigid body, what we do is we take this rigid body as a sum of, as a combination of small constituent parts, and the mass of each part, this is, let's say, delta m, and the position is the position of this part from, let's say, from some center. Let's say this is that coordinate, this is x, y, z. So the position vector of this is along x-axis, that is x1, x2, x3. So this is of delta m, this will be also of delta m, this is also of delta m, this is also of delta m, but the coordinates are different, that is x1, x2, x3, x4. And then the center of mass, that xcm along x-axis, let's say xcm, this is equal to the mass is identical, so that is delta m, and position is x1 plus delta m position is x2, delta m position is x3, and so on, delta m position xn. Total mass, because this is delta m, everywhere there delta m is there, so this is the total mass will be, so that delta m plus delta m plus delta m, so on, n times. So in terms of summation, we can write this is equivalent to summation of delta m multiplied by xi by summation of delta m, and this delta m is the mass of that whole body, so this is equivalent to summation of delta m multiplied by xm by the capital M, where this capital M is the mass of this body. So this is the discrete method, where we have taken individual segments, individual parts as a complete part, and the position is x1, x2, x3, and so on up to xn, and one can write like this. Similarly, along y-axis, what we will do, this RCM is equal to summation of delta m by yi by m, and this is, and ZCM is equivalent to summation of delta m multiplied by zi by the capital M. As a whole, if we take, this is equivalent to RCM in terms of position vector, then this is summation of delta m. So this summation of delta Ri by capital M. So this is the method. Now, if this delta m, this tends to 0, then this concept will convert into integration. So then from the definition of derivatives in differentiation and integration, what we take, this delta m, this is very, very, very small. So when we take this delta m tends to 0, so if this delta m is very small, means that is this delta m tends to 0. It's not 0, it tends to 0, very small, and numbers of particles are huge, and it's a big value, and delta m is very small. Then this xcm, which is equal to summation of delta m xi by capital M, can be converted as equal to, this can be converted as equal to integration of x dm by m. So this is integration of x dm by m, and ycm can be written as equivalent to summation of delta m yi by capital M, can be written as equal to 1 upon m integration of ydm, and similarly ZCM, that is equivalent to integration summation of delta m zi by m, can be written as equivalent to 1 by m zdm, and RCM is finally, that is summation of delta m ri by m, can be written as 1 by m times r. So we use the term, one term is discrete If that system is discrete, means we are taking these segments as an individual part, then we will use this summation. And if that system is taken as continuous, means having one specific density, constant density, and this dm is identical forever and essential. So this if that system is continuous, uniform, then we will use integration, and we have different formula for integration. This is another method of calculation of center of mass, and we will use this now. So this is the formula for calculation of center of mass of an individual system, and what we need is to calculate this delta m dm, means the mass of that small segment, and that coordinate of that dm. If that coordinate of that dm is given, and if this dm, then by integrating and dividing by that total mass, we can calculate the center of mass of that uniform body. So if you are given any uniform body, by using this you can calculate center of mass. We will take some examples. So example number first, let's say. So in spite of a single individual mass, we will take a continuous body and we will calculate the position of center of mass of that body. So before that calculation, we should also know, so density, the term we need to here, because we have to calculate mass. Size is given, so that mass and that size and shape as well as density, these are correlated terms. So we have three types of densities depending on the shape of body. So depending on shape of uniform rigid body, we have three types of densities. Three types of density we will use in calculation depending on type of that body. If that body is linear, first, if body is linear means if that is just a rod, length is given. Then the linear density, the total mass is m, that is represented by lambda. This is equal to the mass by length, means mass per unit length. This is mass per unit length. So obviously unit will be in MKS unit. This is kg per meter. Second, surface density. If that body is two-dimensional, this is that plate of area A. If the length is L, width is B, this is two-dimensional body, just a plate, uniform, of negligible thickness. Then the density is surface density. It is denoted by sigma. Sigma is equal to mass per unit area, and this is equal to mass by length multiplied by B, if length and B is given. And third, obviously that the density, that will be the volume density, but this density term is used in general when we think about that density. This is mass per unit volume. So if that body is 3D body, so if that body is three-dimensional body, so length, width and height is given. So this is just to the density, not volume density, just density. So density is actually taken in general in three-dimensional case, and this is denoted by del rho, and this is equal to mass upon volume. So this is equal to m by L multiplied by B multiplied by H, and here this is kilogram per meter square, and here this is kilogram per meter in SI system unit. Accordingly you can calculate dimension. Okay, so now let us start from one linear system. So this is a rod of mass m, and length is given as capital L, and mass is given as capital M. And for sake of simple calculation, let us pick this in coordinate system. If this is x and this is y, and let's say I should write like this. This is x, and this position is 0, 0. So by using that method of integration, because this body is uniform, density is identical, so by using that integration method we will calculate center of mass. So first the density will be the linear density of rod, that will be the linear density, that is lambda is equal to m by L, mass per unit length. So what we will do, we will take one small segment somewhere here of thickness dx at the position of x. So from the origin at the distance x, we have very small segment, small part, that is the thickness is dx. And now we will calculate the mass of this dx part. Okay, system is along x-axis, so that total xcm we will use this formula, integration of that x dm. We will use this formula because the system is along x-axis only, and the limit is, it is starting from 0 up to L. So in the integration we will use the limit 0 to L. So this x is given. What we have to calculate is this dm. Dm is the mass of this delta x part. So where dm is mass of segment or the part dx, segment of thickness dx. So this will be equal to, so dm is equal to, linear density is this lambda multiplied by that dx. So this is lambda multiplied by dx, and this lambda is, this is m by L multiplied by dx. So when we have this density and that segment, then we can calculate this dm. In the case of surface, we will have this density and multiplied by area. In case of that three-dimensional body, that dm is equivalent to density multiplied by volume. Okay, so for the surface we will take this dA here. For volume we will take dV, that volumetric part, and that density will be rho. So this is m by L here multiplied by dx. Now we will put this here and integrate this. So that xcm is equivalent to 1 by m integration of 0 to L, and this is x. So x multiplied by, this is mx by L multiplied by dx. Now integrate this. So this is xcm, it is equivalent to 1 upon ml, and can be cancelled. Okay. This is 1 upon L, and integration is, this is x dx. So this x dx is x square by 2, because we have this formula, this integration of x to the power n dx. This is equivalent to x n plus 1 by n plus 1. Just simple first formula we have used several times. So this the power will increase by 1. So this will be x square by 2, and we will take that limit 0 to L. So this is 1 by L, and this is L square minus 0 by 2. So this will be equal to L by 2. So this is x. So what we did, just we have calculated this dm in its position and integrate this by using a proper limit of the system, and we have this center of mass. And we know if this is that rod and rod is uniform, then the center of mass will be at the center, and that is L by 2. So by using this calculation method, we have proved the same. So in two-dimensional case also, if we have that plate, we can integrate along x-axis as well as along y-axis, and we can get at that center x and y. So here the one can write this is L by 2 0 center of mass, because if we take that y as 0. Now some more system we can use, and that is so second, let's say we have that rod in half circular shape, means that half ring, one can say. So if this is that ring, we are just taking half ring. So first make ring. This is the complete ring, and just I am taking half of the part. So this is that half ring, and the radius of this ring is, and let's say this is that center, this is 0, and the radius is r. Obviously the mass of this ring is, again let's say capital M, and along x-axis there is nothing. Y-axis, along y-axis this is extended, so that the center of mass will be somewhere situated here. So we will use that y component in this case. Again we have to calculate this YCM is equal to, by using this formula, 1 by m and y multiplied by d. We will use this formula. Why? Because this system is extended along y-axis. So we can think that the center of mass will be situated along this y-axis. That's why this we will take this YCM. XCM is equal to 0. Okay. So first we have to calculate this dm and that y, and put here, and the limit will be, again first we will think that limit will be from this to this. Now we will use the concept of angular distribution. That is small part, we are taking, this is somewhere here, this is that small part. Again we will use that linear density. So that linear density I will use, that lambda is equal to mass per unit length. So first of all I have to use this length. So the total length will be equal to
2 pi r.
Half of 2 pi r.
Pi r.
So that is equal to pi r. So this is equal to mass by pi multiplied by r. So I have this density, it is equal to mass upon pi r. Now this is small segment, and that it is subtending an angle. Angular distribution I am taking, and this angle is, let's say, d theta. This small segment is dx. Okay, so this is dx and this is d theta, and this radius is r, and this angle is, let's say, this is theta. So this is small dx, this is subtending one angle theta from y-axis, and this small angle is d theta. Now if this is theta, this we can have this component along x-axis and y-axis So along x-axis, its component will be r sine theta, and along y-axis, this component is r cos theta. You can take, and this d theta, we can use the definition of angle. So angle is equal to arc upon radius. Angle is d theta. So this is arc is dx. This arc is dx by radius is r. So dx, it is equal to r multiplied by d theta. Clear? So this, now we have this dx, we have this density. So we can have now the dm. Dm is equal to the density multiplied by that small segment dx. So the mass of a small segment dx is equal to, that is dm, it is equal to density multiplied by dx. Okay, just I am repeating the complete term. What we did, we have calculated this lambda. Lambda is equal to mass multiplied by length, mass upon length, and the length is just the half of this parameter, and half of the parameter is pi r, because the complete parameter is 2 pi r. So this lambda is equal to m upon pi r. And then we have calculated this. We have to calculate this dx. So in order to calculate this dx, we have taken this is d theta, that is small angle, and the radius is here. So angle is equal to r upon radius. So this d theta is equal to dx by r, and we have this dx is equal to r theta. So the mass of this part, that is equal to now dm, which is equal to density multiplied by that dx, and density is here. So this is m upon pi r multiplied by this r d theta. So r can be cancelled. So this is equal to m by pi multiplied by d theta. So now what we have, this ycm is equal to 1 upon m, y dm. Now we had this dm is equal to pi multiplied by d theta. And what's about this y? Y is equal to r cos theta. Y is equal to r cos theta. So we will have this ycm is equal to, so here y is equal to r cos theta, the component of that r along y axis. So this ycm can be written as equal to 1 upon m integration of r cos theta, and the dm is equal to m upon pi d theta. So m can be cancelled, and integration of r cos theta by pi multiplied by d theta. Okay, now the limit, main thing is the limit of this integration. So this ring is extended from this to this, and we have taken this angular distribution. So the limit will be in terms of angle. Remember this. So this angle will be, so this angle is, this is minus pi by 2. So taking from this to, this is minus pi by 2 to plus pi by 2 here. So the limit will be from minus pi by 2 to plus pi by 2. Yeah. Okay, clear? So this ring is extended from here to here. So that angular distribution is minus pi by 2 to plus pi by 2. And one can write this is equivalent to 0 to pi by 2 by multiplying this by 2 cos theta by pi theta. This is the formula. If this is the limit is taken as minus pi by 2 to plus pi by 2, then it is can be written as equivalent to 2 multiplied by 0 to pi by 2 r cos theta by pi d theta. And we have integration of this cos theta in terms of output will be in sin theta. So this is equal to r upon pi sin theta from 0 to pi by 2. So one can write this ycm, it is equal to r by pi multiplied by sin theta, it is equal to sin pi by 2 minus sin 0, and you know the value of this sin pi by 2 and sin 0, so this is equal to r by pi. Check the calculation, maybe somewhere some printing mistake है ना, तो देखो कहीं पे कुछ छूटा तो नहीं. is missing here. So this is 2r by pi. मुझे लग रहा था कि वो complete. So this sin pi by 2 is 1 and sin 0 is this. So now this is not a ring, it is a disc. So this is the half disc. Half disc means that mass is uniformly distributed. Areal case. Okay, so the charge density we will take is the surface charge density. Not charge, that density we will take is just that surface density, because this is two-dimensional case. So this is half solid disc of mass. So obviously we will take the same system and start from 0 to this is r, radius is r. So the density will be surface density. We will take. We will consider surface density, that is sigma. It is equivalent to mass is m by surface is we have to calculate area. The total area is pi r square. Just a half करना पड़ेगा, है ना? So this will be pi r square by. Okay, so first part is just calculate that density, surface density. Surface density is mass upon area. Half circle is here, so half circular disc is here, so pi r square by 2. Now we will take that segment dx. We will use that formula YCM, again y axis, because nothing is along x axis, just YCM. So YCM is equivalent to 1 upon m integration of y dy dm. So as usual, our first objective is to find this dm. So dm we will take that small strip, that small segment. So let's say at the position x there is one small strip dx. So from 0, this is that x and this is dx. So we can calculate the mass of this strip. We have to calculate this mass of this strip. So mass of the strip of thickness dx. We will calculate area. Dx is this and that x is this. So just we can calculate this. So how we can calculate? Total, this is half perimeter. Again, half perimeter multiplied by dx. So this is equal to dm is equal to sigma multiplied by dA. I should write. Not sigma. Yeah, sigma. Sigma, this is surface density multiplied by area of that strip. Where I should write mass of the strip of area लिखना चाहिए मुझे, of a small area dA. I should write. So this dm is equal to sigma multiplied by dA, where dA is the area of this strip. So this is equal to sigma multiplied by where dA, it is equal to half perimeter length multiplied by this dx. It is what? This is length multiplied by width. Width is dx. Length is half perimeter. So half perimeter is equal to just pi x. You are getting? Complete perimeter is 2 pi r, and we are just taking half, and this is not r, this is x at the position x. So that perimeter, half perimeter is equal to multiplied by that is pi x multiplied by dx. Getting the point? Half parameter is pi x multiplied by dx. So now we will put this dA here and sigma here, and this dm is equivalent to sigma is m upon pi r square by 2 multiplied by pi x dx. So this is 2m x dx by r square. Okay, now this y. This y is actually the center of this strip, center of mass of this strip, not just that y coordinate. This is the center of the mass of this half ring, one can say. And just earlier we have calculated that center of mass of that half ring. So y is here. Y is position of center of mass of a small ring of thickness dx. So this is equivalent to y is equal to, just there we get that 2r by pi. So here that will be 2x by pi, because x is radius of this ring. So there that the radius was taken as r, here this radius is x, so this y is equivalent to 2x by pi. Just earlier we have taken this 2r by pi, calculated. So that y is the center of mass of that ring of thickness dx, so y is equal to this. Now we will put y and this and integrate. So this ycm is equivalent to 1 upon m, integration of y is 2x by pi multiplied by this 2m x dx by r square. So m will be cancelled, and this is 4 integration of x square dx by pi r square, is it? It will be from 0 to r tak hai na? Angular limit, when we take that angular limit from, then that will be minus pi by 2, but here we have not taken that in form of angular distribution. So linear distribution is there, so the limit is from 0 to r. So the limit is 0 to r. Let's take this x cube by 3, and by using that formula we have this is equal to ycm, it's equal to 4 pi r square multiplied by x cube by 3 from 0 to r. One order enhancement, x square is x cube. So this is 4 pi r square, and that is r cube by 3 minus 0, and this is 4r by pi, 3 pi. 4 by 3, pi is here, r will be cancelled. So this is y. Check the calculation. So the method of practice is, first of all you have to calculate dm, the mass of that is small part, then integrate it. But before that integration you have to take that the second term y also, if along y-axis, along x-axis, then you have to take that x, and 3D case that may be different from x or y. So you should make some formula related to 3D system. Just to take up just half disk. In place of this, if we have this half circular disk like this, radius r. Okay, so in this case we will take one strip here somewhere at the x, and we will calculate dm for this. We will calculate dm for this. So volume charge volume density we will take dx is the thickness, x is here. So in terms of x, you have to calculate that volumetric term and find out dA. So little bit complicated, but not very difficult. You can. Okay, I think this is more than enough for today's lecture. Thank you.